In this video, we show you the deformable transformers for end-to-end object detection. The paper was published at 2021 as a conference paper. The deformable DETR is proposed to mitigate two issues in the original DETR model: the slow convergence and the limited feature spatial resolution. The original DETR, proposed by Nicholas Guerin and others in 2020, is a method that views object detection as a direct set prediction problem. The goal of object detection is to predict a set of bounding box and category labels for each object of interest. The main ingredients of the framework called detection transformer, or DETR, are a set-based global laws that force unique predictions via bipartite matching and a transformer encoder-decoder architecture. Given a fixed small set of learned object queries, DETR reasons about the relations of the objects and the global image contexts to directly output the final set of predictors in parallel. DETR directly predicts the final set of detections by combining a common convolutional neural network with a transformer architecture. During training, bipartite matching uniquely assigns predictions with ground truth boxes. Prediction with no match should yield a no object empty class prediction. DTR uses a conventional convolutional neural network backbone to learn a 2D representation of an input image. The model flattens it and supplements it with a positional encoding before passing it into a transformer encoder. A transformer decoder then takes an input as a small fixed number of learned positional embeddings, which we call object queries, and additionally attends to the encoder output. Then they pass each output embedding of the decoder to a shared feed-forward network that predicts either a detection, class, and bounding box, or a no object class. Attention mechanisms are neural network layers that aggregate information from the entire input sequence. Transformers introduce the self-attention layers, which, similarly to non-local neural networks, scan through each element of a sequence and update it by aggregate information from the broader sequence. One of the main advantages of attention-based models is their global computations and perfect memory, which makes them more suitable than RNNs on long sequence. RNNs are recurrent neural networks. No end-to-end object detectors require NMS to remove redundant predictions, as the last one manually designed component in the object detection pipeline. Non-differentiable NMS blocks set up an end-to-end object detection system. Let's go back to the proposal deformable transformers for end-to-end object detection. This is an illustration of the proposed deformable DETR object detector. The proposed deformable attention module is inspired by deformable convolution and belongs to the category of learned data in the dependent sparse attention. It only focuses on the small fixed set of sampling points predicted from the future of query elements. One of the main difficulties in object detection is to effectively represent objects at vastly different scales. The proposed multi-scale deformable attention module can naturally aggregate multi-scale feature maps via attention mechanism without the help of these future parent networks. The core issue of applying transform attention on image future maps is that it would look over all possible spatial locations. To address this, it is presented the deformable attention model. Inspired by deformable convolution, the deformable attention model only attends to a small set of key sampling points around a reference point, regardless of the spatial size of the future maps. By assigning only a small fixed number of keys for each query, the issues of convergence and the future spatial resolution can be mitigated. The experiments were taken using the COCO dataset. In this illustration, there is a comparison of deformable DETR with the original DETR. As we can see, the original DETR needs 500 epochs to give similar results presented by the deformable DETR in only 50 epochs. The original DETR needs 2000 GPU training hours, while the deformable DETR needs only 325 hours of GPU training. In this table, we can see the comparison of the deformable DETR with the state-of-art methods applied in COCO 2017. As you can see, the deformable DETR produces similar results in comparison with the best models. This illustration shows the gradient norm of each item in final detection result with respect to each pixel in input image. Now you can see the multi-scale deformable attention. Its sampling point is marked as a filled circle whose colors indicates its corresponding attention weight. The reference pointer is shown as green cross marker, which is also equivalent to query point in encoder. In the encoder, the predicted bounding box is shown as a green rectangle. In conclusion, the author says that the deformable DETR is an end-to-end object detector that is meant to be efficient and fast conversion. It enables the users to explore more interesting and practical variants of end-to-end object detectors. At the core of the deformable DETR are the multi-scale deformable attention modules, which is an efficient attention mechanism in processing image feature maps. The authors hope their work opens up new possibilities in exploring end-to-end object detection. This video was presented by me, Roberto Carlos dos Santos, Master Degree student at Universidade do Estado do Rio de Janeiro. Scomp IME WERJ 2021, first period, deep learning class. The master teacher is Gilson Oswald Pedro Costa. Thank you.